pleasure for me to give this presentation, which is also a way to celebrate the work of Gérald Desrosiers in particular, who retired a few years ago. So this talk is about innovation-based estimates of error covariances, and I'm going to review this by presenting some historical works in a non-exhaustive way, mostly corresponding to those applied for operational NWP. So here is the outline of the talk. After the introduction, I will present the method based on covariances of analysis residuals, and then their spectral interpretation, followed by the method based on the minimum of the cost function, before illustrating some comparison with ensemble information and some conclusions. So we can start with the introduction to innovation covariances. So the general framework here is based on the statistical linear estimation, in which the analysis XA is written as being equal to the background plus an analysis increment delta X. And this increment delta X is given by the product between the Kalman gain K and the innovation D, where D is the difference between the observation and the background projected into observation space by the nonlinear observation operator H. And the gain matrix depends on B and R, which are the covariances of background and observation errors, respectively. And this analysis increment delta X is also the solution of a variational problem, which is based on the cost function J, which is classically written as the sum of background term JB and an observation term JO. So a basic question in this context is, how can we estimate the error covariances? And to some extent, this is quite difficult because the true atmospheric state is never exactly known. However, it can be considered to use observation minus background departures in order to estimate some average variances and correlations of R and B using assumptions on the spatial structures of the errors. Moreover, it is possible to use an ensemble in order to simulate the error evolution and to estimate some space and time-dependent background error structures. In the end, it remains needed also to use some covariance modeling in order to filter out sampling noise and other uncertainties in the ensemble. So, if we look at innovations, they can be expanded as a function of the true state HXT in order to express them as the difference between observation errors and EO and background errors EB projected onto observation space by the nonlinear version of the observation operator H. It can be mentioned also that the observation errors contains two components. One is the instrument error, and the other one is the error associated to the observation operator. So this allows the innovation covariances to be written as the sum of observation error covariances R and background error covariances projected onto observation space, assuming that observation errors and background errors are uncorrelated and with each other and unbiased. So this is the classical work of Rutherford and Hollingsworth and Lorberg. And the principle is illustrated here also under the additional assumption that observation errors are spatially uncorrelated. It is possible to interpret the spatial covariances of innovations at non-zero separation distance as corresponding to background error covariances. Moreover, it is possible to extrapolate these innovation covariances towards the zero separation distance in order to partition the innovation variance into observational variance and background error variance contributions. So beyond this first historical work, a possibility to estimate the error covariances is also to use covariances of analysis residuals. This is not the first work of Gérald Desrosiers about this kind of approach, but it is now the most emblematic one. So if we follow the notations used in this slide, the analysis increment in observation space, DAB, can be written as the product between the innovation D and the gain matrix HK, which can be expanded as function of background and observation error covariances. And this allows the covariance between the analysis increment DAB and the innovation to be written like this, where appears the innovation covariance EDD/DT. And then it can be shown that if all the covariances are exact and optimal, there will be a cancellation between the inverse of the innovation covariance matrix here and the direct innovation covariance matrix here. So in this case, this covariance between analysis increment and innovation is equal to the true background error covariance in observation space. Similarly, it is possible to relate the observation error covariance matrix with the covariance between the OBS minus analysis departure and the innovation following these derivations. So this is illustrated here in a geometric way by considering this kind of triangle with background XB, analysis XA, observation YO, and the true state XT. Actually, following the Euclid theorem, it can be shown that the product between the innovation D and its component DAB, which is the analysis increment, is equal to the square of epsilon B corresponding to the background error variance. So this is a slide that summarizes some features of the practical implementation of this approach. A typical feature is that there are no multiple statistical realizations of D, DOA, DBA for a given analysis. For this reason, an ergodicity hypothesis is necessary, usually leading to spatial averaging of diagnosed variances and covariances. The practical computation is relatively simple. For instance, for sigma square, this is the sum of the cross product between observation minus analysis departures with the innovations divided by the number P of observations. So this is rather easy to implement, especially to try to diagnose observation error variances and covariances. It must be noticed that the use of estimated global variance and correlation length scale potentially includes implicit summing of adjusted eigenvalues, which plays an important role in the relevance of the diagnosis, as will be detailed in the page 15 of this presentation. So this is an illustration of the result of this kind of approach in a 1D idealized context, where true sigma O and true sigma B are both equal to 1. We have uncorrelated observation errors and spatially correlated background errors. And so when starting from overestimated observation error variances and underestimated background error variances, it is possible to converge when iterating the diagnosis towards the true values equal to 1 for both sigma O's and sigma B's. Moreover, the bottom panels indicate that even if we use suboptimal sigma B's, either underestimated or overestimating, and if we only adjust the sigma O's, it is still possible to get the optimal values of sigma O's to a large extent. So this kind of simple illustration has been further studied also in other papers like Lee et al. 2009 in other configurations. And this is another illustration of the method in order to retrieve Yazi interchannel error correlations. So this is taken from a paper by Niels Bormann at ISMWF. And so this figure shows the results provided by 3 different methods about these interchannel error correlation. And it can be noticed that they look relatively consistent with each other. And so this may give some confidence in the results of this kind of diagnostics. And it must be noticed that this kind of inter-channel error correlations are now used in many NWP centers. It is important to consider a spectral interpretation of these diagnostics. So to do this, one can consider a single set of observations at every grid point of the domain with some homogeneous B and R covariances. And so in this case, the observation operator is simply the identity matrix, and the background error covariances and the observation error covariances are diagonal matrices in spectral space with eigenvalues equal to lambda B and lambda O respectively. And so in this case, the product between the inverse of the innovation covariance specified and the true innovation covariance matrix can be expressed in spectral space as a function of a scale-dependent ratio, which is written here, which is the ratio between the true innovation eigenvalues and the specified innovation eigenvalues. So this is interesting to consider in the iterative procedure. Actually, it can be shown that implicitly we can consider this implicit scale-dependent diagnostic ratio, lambda R, which is this ratio between true eigenvalues and specified innovation eigenvalues. And then it can be considered that there is an implicit scale-dependent adjustment of the specified eigenvalues, which amounts to multiplying the specified eigenvalues with this diagnostic scale-dependent ratio. And another step is to compute the total variance, so for background errors, for instance, which is amounts to implicitly summing all the adjusted eigenvalues. So this is interesting to consider for examples where we have a red spectrum in B and a white spectrum in R, and more generally when we have scale differences between B and R. So in this case, in the large scales, which are the main contribution to the background error variance, the background eigenvalues will be much larger than the observational eigenvalues. So this means that the scale-dependent ratio will be close to a ratio between true background eigenvalues and specified background eigenvalues. And using this ratio allows the large-scale background eigenvalues to be implicitly adjusted towards the true background eigenvalues. And then through the eigenvalue summing, which is dominated by the large-scale eigenvalues, this leads to more realistic background error variances. Conversely, in the small scales, the background eigenvalues are much smaller than the observational eigenvalues, which means that the scale-dependent ratio, lambda R, will be close to the ratio between the true observation eigenvalues and the specified observation eigenvalues. And this allows the diagnosed observation error variance to be made close to the exact one. So this has been studied partly by Gérald Desrosiers in 2005 and also by authors like Citwell and Ménard in 2020. So this is an illustration, again, in a 1D idealized context. So still with sigma O's and sigma B's equal to 1, spatially uncorrelated observation errors, spatially correlated background errors. And so in the left panel, we have these different eigenvalues. We can see in blue that specified background eigenvalues are underestimated compared to the true eigenvalues in red. And then when applying the scale-dependent adjusted eigenvalue ratio, we obtain the green curve of eigenvalues for the background, which are now closer to the true background eigenvalues. And this, when summing all the green eigenvalues, this allows to provide a sigma B value that is closer to the exact value of the variance. And this is further improved when iterating the diagnosis, as shown by the 0.85 value inside the circle. Similarly, for observation error variances, we can see with the blue line that the observation error variances are overestimated. And then when applying the scale-dependent ratio, this is improved by providing the green curve, which correspond to diagnosed eigenvalues, which are close to the exact observation eigenvalues. Even if the adjustment is the somewhat opposite in the very first small wave numbers. And so when summing all the green eigenvalues, we obtain a sigma estimate, which is now close to the exact one. This is another illustration when considering observation errors that are spatially correlated. And the behavior can be shown to be relatively similar with these adjustments towards the true observation eigenvalues, but the convergence can be shown to be somewhat slower, as shown by the figures inside these circles. It can be also considered in this idealized context the effect of misspecified observation error correlations. So this is the case where the specified observation error covariance matrix is based on an assumption of spatially uncorrelated observation errors, whereas the true observation error correlations are correlated. And in this case, we can see that the sigma diagnosis is still somewhat improved during the first iterations, but they tend to converge towards suboptimal values, as shown by this figure here. And this has been investigated by authors like Waller et al. And this can be again understood or examined in spectral space. For instance, in the second iteration, we can see that the adjusted eigenvalues in the large scales tend to be underestimated compared to the true observation eigenvalues in red due to the neglect of the observation error correlations. It can be considered also to diagnose the observation error correlation length scale using this kind of approach. So the difference with the previous slide is now that the observation error length scale is diagnosed from the updated eigenvalues in order to redefine the observation error correlation eigenvalues. So the results are illustrated in this simple example, starting from specified uncorrelated observation errors. And then using the diagnostics, it can be seen that the diagnostic method is able to provide accurate estimates of the observation error length scale after a few iterations. So beyond this method of covariances of analysis residuals, another approach is to use the minimum of the cost function. This is a methodology which has been used or introduced a bit before the first one. And indeed, it has been shown by Olivier Tarragland around 2000 that the value of the cost function at its minimum can be expanded as a function of the analysis increment delta x a, and then by expressing the analysis increment as a function of the innovation d times the gain matrix k and a few more derivations, it can be shown that this minimum of the cost function is simply equal to the inner product of the innovation d with itself, weighted by the inverse of the specified innovation covariance matrix D. So this allows to compute the statistical expectation of J mean, which can be shown to be equal to P, which is the number of observations under the condition that the specified innovation covariance matrix is equal to the true innovation covariance matrix. It must be mentioned that this is an unnecessary criterion in the sense that if both background error covariances and observation error covariances are misspecified by the same factor alpha, then the analysis increment delta x will be still optimal, but the expectation of Jamie will be equal to p divided by alpha. It is also possible to derive the expectation of the subparts of J-mean. So for the JB part, it can be shown that the expectation is a trace of HK, which is the total DFS, that is the degrees of freedom for a signal. So this is the number of degrees of freedom provided by observations to deviate from the background during the analysis step. And then we have similar expression for the JO part and its subcomponents, which I will not detail here. Difficulty is that matrix K is not explicitly computed in a variational assimilation. However, as shown by Gérald Desrosiers and his colleagues, it is possible to compute the trace of HK using a Monte Carlo procedure, using some observations perturbations, delta YO, and associated analysis, perturbed analysis increment, delta XA. So using this kind of simple products, it is possible to estimate the trace of HK. And the observation perturbations are constructing as random draws of the specified observation error covariance matrix R. So this can be used to conduct some tuning of the error variances, for instance, using a scaling factor for the B matrix SB squared, which is simply equal to the expectation of JB, so in the sense of average effective values of JB, divided by the trace of HK. And you have a similar formula for the observation error variance scaling factor. And the results are illustrated here for different observation types in sigma O's in terms of normalization coefficients in the Meteor-France arpège for DVAR. So you can see that the scaling factor tends to be smaller than 1, which indicates that specified observation error variances tend to be overestimated in this case. Another important aspect to consider is the possibility to compare these estimates with ensemble information. So this is illustrated here by considering the comparison between innovation-based estimate using the Desrosiers diagnostics with ensemble estimate of sigma b's of temperature. So this is plotted here as a function of height. So the dashed line is the innovation-based sigma b's of temperature, which indicate that sigma b's tend to increase in the boundary layer in relation with large model uncertainties at these levels. And the full line is the ensemble-based sigma b of temperature in the case where multiplicative inflation is used to simulate the model error contributions. So it can be seen that the ensemble sigma b's exhibit a different variation in the boundary layer corresponding to a decrease. And so the difference between these two curves may point out to some deficiencies in the multiplicative inflation procedure, which does not seem to represent well the model error contributions in the low levels. And this is interesting to compare with the right panel, which displays the case of an ensemble that includes random model parameter perturbations, including at low levels, in order to represent the model error contributions. So in this case, we can see that the general vertical variations of the specified and diagnosed sigma b's are consistent with each other, with this increase in the low levels in particular, thanks to the model perturbations in the boundary layer. So in other words, using such innovation-based diagnostics allows different ensembles to be compared and evaluated with observation errors accounted for. So this has been provided by Nicole Gerardo at Meteor-France. Another application is the possibility to diagnose recent model error contributions in data assimilation cycling. So this is illustrated here by considering the contributions to short-range forecast error variance with observation error contributions accumulated during several cycles and model error contributions. And so what can be done is to estimate this short-range innovation forecast error variance with innovation-based diagnostics, such as the de Rosier approach. The observation error contributions can be estimated by an ISDA with observation perturbations only, and then the model error contributions can be estimated by computing the difference between the innovation-based estimates and the observation error contributions. And so this is illustrated in terms of results. So in red, we have observation error contributions, which indicate that the observation error contributions are significant, but they tend to be smaller than model error contributions, especially at low levels. So conclusions. So the covariance of analysis residuals are rather easy to implement in order to estimate R or to tune B. They give apparently reasonable results in many cases. The J-mean diagnostics are linked with basic foundations of blue estimation, and they can be used to tune the weights of R and B matrices too. It is important to consider the scale differences in the error contributions, and this can be examined by using a spectral formalism, and also to consider the implicit scale-dependent adjustment of eigenvalues and the eigenvalue summing, which are important steps in the diagnosis. This can be used to compare the diagnostics with ensemble information with observation errors accounted for in order to examine vertical variations of background errors and deviations, and also in order to estimate some model error contributions. And then I have a last slide just with some references on the subject, including some of them related to model error diagnostics and links with other approaches like likelihood approaches and cross-validation. Okay, so thank you for your attention. I will be pleased to answer your questions.
Yeah, thank you very much, Loïk, for this very nice overview of the work which has been done in this domain. The questions I would have a question about if the Rosier method, which we're actually using quite abundantly at the German Weather Service, and but we're actually because we can change R, we're not, when we're cycling the de Rosier method, we cannot adjust the B matrix, so it's just the R matrix, and therefore at each cycle what we are taking is we're making sure that de Rosier gives us an estimate for R and B in observation space, and we make sure at every cycle that the ratio between the R and the B we're using is the same as the ratio which you get from the de Rosier method. Have you, yeah, when you're just adjusting R, don't you think it's dangerous that you and the B matrix which you cannot change is wrong, that you get into wrong converge towards a wrong value?
Yes, I agree. Yes, it is the ratio between the two quantities which is important in the end. Mm. And you could say also that the absolute values is still important potentially for quality control decisions, because this is specified in terms of multiplicative factor of the observation errors and deviations and background errors and deviations. But for the minimization or the analysis computation in the end, it is the ratio which is the most important one. So I agree that diagnosing both sigma B's and sigma O's is important. Yeah.
Yeah, thank you. Do we have another question from the chat? Yeah, otherwise, I would have another question actually. When you were using you said something about problems with these, you mentioned, I think it was work from Waller et al. About that when you specify the correlations of R wrongly, that you have some problems with the divergence. Did I get that right? Yes. And we could explain when we are using the de Rosier method for ISDA channels, for interchannel correlations, you've shown an example of, then we are, I think we are not cycling it at all, and I don't think other centers are cycling the de Rosier method very much there.
Okay.
Could that be a reason that when you have a whole non-diagonal matrix, that it's more problematic, the cycling? Would that be?
Yes, I would guess that maybe the best approach is to get a first estimate of these interchannel error collections, then to implement them in the assimilation scheme, and after some time to diagnose again the interchannel error correlations. Because in principle, this is the way it is expected to converge, whereas if you neglect the error correlations, you know that the diagnosed correlations will be suboptimal. So in our case at Meteor France, I think we are trying to update this kind of intentional error correlations from time to time. So maybe not like something like every new cycle, but something like this. And so from my point of view, that could be a better approach than neglecting the error correlations.
Yeah, thank you much. It's a very nice overview over these very important methods, which in our, well, I think in practice are used by many operational centers, actually. Yeah. So if I don't miss any questions there, I think I'm announcing I'm welcoming the next speaker, which is